All right, so we started with the mash. We talked about why we needed the grain to be malted. So why do we need the grain to be malted? Why do we have to malt the grain first? Why do we have to malt our grain?
Clean, no.
What's happening? What is that water doing to the grain? It's what? Yeah, okay, so it'll help to clean. I'm pretty dirty when it comes to mashing. Believe it or not. Like I don't wash my mash tun, I just rinse it out. Because it gets boiled, right? Boil is gonna be sanitizing for me. What is that? What happens when we get the grains wet? What ultimately happens?
Seeds germinate.
Seeds germinate, all right? When the seeds germinate, what becomes active? The enzymes, all right? And then how do we stop the germination process? We dry them. All right, so now we have our dried grain and we are going to start the mash. All right, so we're going to talk about mashing right now. And what we're going to talk about with the mashing is this interplay between the enzymes that are there and temperature. All right, enzymes and temperature. All right, so what's going to happen is that we mix the grains with the water, and then we want a temperature of that entire mixture to be in a specific range. All right, so our optimum temperatures that we are targeting is between 140 and 158 degrees Fahrenheit. Right. Not only that, but we also have to worry about pHs. So pH is a measure of acidity. It's a measure of how many hydrogen ions are really in our solution. All right, something that's more acidic, all right, you've got more hydrogen ions. Water is close to neutral, so distilled water is neutral. It's right at 7. All right, it's our middle point. Our tap water is probably out at like pH of 7.8 to 8. All right, so it means we've got other things in there that's affecting the pH. Our mash temperature or mash pH that we're targeting is 5.4 to 5.6. So why do we want these temperatures and these pHs? It's because these temperatures and these pHs are the best for the enzymes that we have in there, and it's best for them because they're going to be doing the best work that they possibly can, the most efficient work that they can do. All right. So what our primary focus is on the starches. The starch degradation, that's what we're dealing with. Most of our starches exist in branched form. I'm going to add lines to all of these and show you branching patterns. So these are all connected through bonds. These are all just regular glucose sugar molecules, but they are linked to form a specific type of bond that forms a starch molecule. All right. So we said yesterday that this is amylopectin. Amylopectin. It's highly branched glucose molecules. All right. I can do this as well. Branching down like that. Highly branched. We also have unbranching sugar molecules. And I'm not going to do circles. I'm just going to say these unbranching ones tend to exist as a coil. And this is amylose. Amylopectin, amylose. All right. There's no branching on it. It's just one long chain of glucose. All right. One long chain of glucose. So our amylopectin is this branching starch. All right. If we take this amylopectin, all right, and we break it down, we can get different types of molecules with it. So if we get a single molecule, single sugar, that is our glucose. One of those circles represents a glucose molecule. This glucose is easily fermentable. And not just easily, 100% of it can be fermented, which means the yeast can take this glucose, utilize it as a fuel source, and produce our alcohol, produce our CO2. Sometimes this degradation will give us two of these molecules that are linked. This is maltose. This has our two glucose molecules. All right. This is also easily fermentable. But our yeast love this stuff. They'll consume the glucose, but they absolutely love maltose. We can also get a 3-chain molecule. Now, I'm going to say this is at the end of our mash. So if we do the mash properly, we've got our optimum temperatures, optimum pH. We're going to be producing these 3 things. All right. If we just do the mash for, let's say, 5 minutes, we're going to produce a lot more. We can produce much longer chains as well. But mostly we get our 1-chain glucose, our 2-chain maltose, and our 3-chain is triose. That's our 3 glucose molecules. This chain is harder for yeast to use. It's harder for the yeast to use. Some yeast can't use it. Some yeast can't use this triose molecule. Which type of yeasts can't use it? Some of the English yeasts. The English ale yeast can't use it. And that has an effect then, because if the yeast can't use that molecule, then it stays in the final product. It lends a sweetness. If we taste each of these, we will taste them and we will perceive them as being sweet. If this is left in the beer, in those English ales, we're going to be left with a sweeter type of beer. And that kind of is what defines some of those styles. But we have one more thing that is out there. And this is just an example of one. We can be left with something like this, which is our glucose molecule that still has a branch on it. Right? It hasn't been busted up completely. Things like this just have a generic name called limit dextrins. Limit dextrins. All right. These things are considered unfermentable. The yeast can't use them. It can't break it down to produce our sugars, or to produce our alcohol and CO2. They're unfermentable, yet they're still in the beer. So what is their role? Any guess? What would be their role? They do play an important role. They contribute something called mouthfeel. Mouthfeel to the beer. So there is something that I want you to take away from this class. You can go on and never try beer at all for the rest of your life. But there is one thing that I want you to always remember. Color of the beer has nothing to do with mouthfeel. All right? Mouthfeel is how thick you perceive that beer. A beer that you perceive as being very thick and heavy is one that's going to have a lot of these limit dextrins in it. A beer that is very light and thin is a beer that has very few of these limit dextrins in it. All right? We can manipulate how many of these limit dextrins we have in our beer by adjusting our temperatures. All right? So one thing that I hear, and I don't know if you've heard it at your parents, cousins, wherever, you may have heard some people say, I don't like dark beers because they're thick. And that's not true. Not all dark beers are going to have that thick taste. Not all light beers are going to have a very light and watery taste or mouthfeel. It entirely depends on how many of these limit dextrins we have in our actual beer. All right? So what about these temperatures? Anyone have questions here? All right, so what about these temperatures? Our temperatures, most important, are going to be the alpha and beta amylases. The alpha and beta amylases are going to be the ones that basically break up our pectins, our amylopectins. All right? What's the difference between the two? Well, the difference comes down to how they chop up. All right? So beta amylase is a lot like Pac-Man. Who knows who Pac-Man is? Some people. If you've seen the movie Pixels, you've seen Pac-Man. It's an old video game. All right? Pac-Man goes around and just chomps these little, I don't even know what they call them. Little white dots in the game or something like that. That's basically what our beta amylase is going to do. All right? So I say it's kind of like Pac-Man. Another one is hedge trimmers. And how does that work? We go back to our amylopectin. What beta amylase is going to do is going to come over and it's going to chop at the ends. And it's going to chop, chop, chop. But it can only chop at the free ends. So what I'm going to do is make a whole new chain. And say this is amylose, so no branches. Pac-Man beta amylase is going to come over, start at the end, and chop, chop, chop. And it's going to produce a bunch of these maltose. That's what it does. But there's a limit. There's a limit. It can only get within three sugars of our branch points. All right? It can only get within 3 sugars of our branch points. So this spot here isn't quite what it can do because that's within 3. But it could cut there and produce that maltose. All right? Because that's considered our main chain. All right? This is a branch. It can't cut any of those. Our main chain, here's our main chain. All right? It can come in